Hello everyone, once again welcome to my YouTube channel Physics with Dr. Sanjay Bhargav. In this chapter of moving charges and magnetism part 4, we are going to discuss about force on a current carrying conductor placed in a magnetic field, force between two parallel currents. We'll provide a definition of ampere, also discuss the calculation of torque on a current loop. We'll discuss magnetic dipole and then talk about circular current loop behaving like a magnetic dipole. Now let us begin with force on a current carrying conductor in a magnetic field. So we consider a current carrying conductor of length dl. This represents a conductor of length dl. Cross-sectional area A. So A represents here the cross-sectional area. It carries a current I. Is placed in the plane of a paper. Now, the magnetic field is represented here by the cross, which means the magnetic field is perpendicular to the plane of the paper and inwards. When a current carrying conductor is placed in a magnetic field, the moving electrons experience a force. Since the electrons cannot move outside the conductor, what do? They transfer their force to the conductor through collisions with the atoms of conductor. Thus, conductor experiences a force. So हम क्या बोल रहे हैं यहाँ पर? हमने एक कंडक्टर ले लिया जिसका लेंथ dl है, क्रॉस सेक्शनल एरिया a है और उसमें से एक I करंट हम पास करते हैं. इसमें जो फ्री इलेक्ट्रॉन्स हैं वो जब मैग्नेटिक फील्ड में रहते हैं तो उन पर एक फोर्स लगता है. ये इलेक्ट्रॉन्स कंडक्टर के बाहर नहीं आ सकते, इसीलिए ये अपने फोर्स, इस पर जो फोर्स है उसको कंडक्टर की वॉल्स पर ट्रांसफर करते हैं थ्रू कोलिजन्स विद द एटम्स ऑफ अ कंडक्टर, और इसके कारण कंडक्टर पर एक फोर्स लगता है. इस फोर्स का वैल्यू हमें कैलकुलेट करना है. तो उसके कैलकुलेशन के लिए व्हाट डू वी अज्यूम? वी अज्यूम स्मॉल n as the number of electrons per unit volume, that is number density of electrons. Vd represents the drift speed of the electrons, that is the average velocity that is acquired by the free electrons in the presence of electric field would be called as drift velocity. A is the area of cross section of the conductor. Now I can calculate what would be the force on each electron, that is given by Fm, and that is Q into V cross B. We used to calculate it by Q into V cross B. So charge on the electron minus E, velocity of the electron Vd, and kept in a magnetic field B. The direction of the force is opposite to Vd cross B, as electrons have a negative charge. So whatever is the direction given by Vd cross B, then electrons would experience a force opposite to that direction. जो भी डायरेक्शन आएगा फोर्स का Vd क्रॉस B से, तो इलेक्ट्रॉन पर लगने वाला फोर्स उसके एग्जैक्टली ऑपोजिट आएगा, क्योंकि इलेक्ट्रॉन पर एक नेगेटिव चार्ज रहता है. The total number of electrons in a conductor. So total number of electrons in a conductor is equal to volume into number density. So number density given by small l n and volume of the conductor given by A into dl. तो इससे हम क्या करते हैं? एक कंडक्टर के dl सेक्शन में कितने इलेक्ट्रॉन्स हैं उनका वैल्यू कैलकुलेट करते हैं, क्योंकि हमें मालूम है एक इलेक्ट्रॉन पर कितना फोर्स है. हमें ये भी मालूम है कि व्हाट आर द नंबर ऑफ इलेक्ट्रॉन्स इन अ कंडक्टर. सो टोटल फोर्स अगर मुझे कैलकुलेट करना है तो मुझे नंबर ऑफ इलेक्ट्रॉन्स को फोर्स ऑन ईच इलेक्ट्रॉन से मल्टीप्लाई करना पड़ेगा. सो आई कैन कैलकुलेट हियर द टोटल फोर्स एक्टिंग ऑन ऑल द इलेक्ट्रॉन्स. सो दैट इज गिवन बाय df. NADL, the number of electrons, and Fm is force on each electron. So minus NEADL Vd cross B. So this can be written as minus NEA dl Vd cross B. Now I is NEA Vd. And what is Vd? That is equal to minus dl by dt. What does the negative sign tell me? It shows that Vd and dl are in opposite direction. Electrons have a velocity opposite to dl. So df can be written as minus NEA dl, and instead of Vd I am writing minus dl by dt cross B. Minus and minus sign make it positive, and then I can be allowed to write NEA dl by dt into dl cross B. And dl by dt is nothing but Vd. We are talking about the magnitude of the velocity. So NEA Vd dl cross B. It would be equal to I into dl cross B. This equation gives the force that is experienced by a current carrying conductor of length dl. Now what would be the total force on a conductor of length? It can be obtained by integration over the length. So total force would be given by integration df would be equal to I integration of dl cross B, and the integration dl means the total length of the conductor, which makes me write F is equal to I into L cross B. The direction of the force is given by either Fleming's left hand rule or the right hand palm rule. What does the Fleming's left hand rule say? Hold the forefinger, middle finger and the thumb of the left hand in three mutually perpendicular directions. If the forefinger points in the direction of magnetic field, middle finger points in the direction of current, then the thumb points in the direction of force as shown in the figure. So let us first look at the figure. This one. This represents the left hand rule. Forefinger in the direction of magnetic field, middle finger in the direction of flow of positive charge or the current, then the thumb automatically points in the direction of force. The other way of determination of a direction of magnetic field is through the right hand palm rule. What does it say? If all the fingers of the right hand point in the direction of magnetic field, thumb points in the direction of current, then the palm faces in the direction of force. So out of the two methods, you can use any to calculate what would be the direction of the force on the electron or a conductor which has been placed in a magnetic field. Now, we would like to discuss what would be the value of force between two parallel currents. So here we are having two conductors here, conductor A and conductor B. The distance between the two conductors is small d. IA is the current in the first conductor and IB is the current in the second conductor. So IA and IB are the currents in the two conductors. We are considering a section of length L here. So let us read. We consider two conductors A and B separated by a distance d carrying parallel currents IA and IB respectively. The current in conductor A produces magnetic field BA at all points along the conductor B. That is, I can imagine that the conductor B carrying a current IB is placed in the magnetic field produced by the first conductor. So let us calculate first the magnetic field due to current IA. So for a straight conductor, the magnetic field is given by mu 0 I upon 2 pi d. So here it is mu 0 IA upon 2 pi d. What would be the direction of BA? The direction can always be calculated by the right hand rule, and it comes out as downward according to the right hand rule. And what does the right hand rule say? Curl the fingers around the conductor, thumb points in the direction of current, then the curling finger points in the direction of magnetic field. The conductor B carrying a current IB will experience a sideward force FBA towards conductor A. The magnitude of the force given by IL cross B. So IB is the current in the conductor, L is the length of it placed in the magnetic field of the first conductor. So I get IB LBA sine theta. In this case, what does theta represent? It represents the angle between length and BA vector, which is 90 in our case. So sine 90 would be equal to 1. So force on B due to A is given by IB LBA, and that can be written as mu 0 IA IB upon 2 pi d L. Similarly, I can calculate what would be the force on conductor A due to magnetic field produced by current in the conductor B. Both the forces are equal in magnitude and are directed opposite to each other. That is why we write FBA is equal to minus FAB. Let us look at the direction of the forces. So FBA is towards the conductor A, and what would be the direction of FAB? That would be towards the conductor B. So I can say the currents flowing in the same direction attract each other. And another important result is similarly oppositely directed currents, they repel each other. So rule says parallel currents attract and anti-parallel currents repel. You can always prove anti-parallel currents repel each other. A very important observation here in the form of a note which says this rule is opposite to that of electrostatics. Like charges having the same sign, they repel each other. But like parallel currents, they attract each other. This equation can be utilized to define a standard ampere. That means I am talking about the equation force BA is equal to mu 0 IA IB L upon 2 pi d. This equation would be utilized to define 1 ampere of a current. Let the force FBA be the force per unit length, and it would be mu 0 IA IB upon 2 pi d. Let IA and IB equal to 1 ampere, D is equal to 1 meter, then FBA is 2 into 10 raised to power minus 7 Newton per meter. 1 ampere is the value of that steady current which, when maintained in each of the two very long straight parallel conductors of negligible cross section which are placed 1 meter apart in vacuum, will produce on each of these conductors a force of 2 into 10 raised to power minus 7 Newton per meter of length. So how do I define 1 ampere? 1 ampere is the value of current that steady current which, when maintained in each of the two very long straight parallel conductors of negligible cross section and are placed 1 meter apart in vacuum, will produce a force on each of these conductors a force equal to 2 into 10 raised to power minus 7 Newton per meter of length. So this is the standard definition of ampere. Now what we want is, we need to calculate what would be the torque on a current loop, and we'll show that each current loop will behave like a magnetic dipole. Case 1. A rectangular loop is placed such that magnetic field is in the plane of the loop, this way. So this represents the figure for case 1. The plane of the loop is in the direction of a magnetic field. We consider a rectangular coil of length A, breadth B, carrying a current I in clockwise direction, and is placed in a uniform magnetic field produced by the two pole pieces of the magnet. The number of turns in the coil is N, and its cross-sectional area is a capital A. The field exerts no force on the two arms AD and BC of the loop. Why? Because these two arms are parallel to the direction of a magnetic field. So one of the arm is parallel, another is anti-parallel, making an angle either of 0 or 180. And remember, sine 0 is also 0 and sine 180 is also 0. Therefore, the force on conductor AB and BC would be equal to 0. Now what happens to the force on conductor AB? F1 would be equal to I small b, b sine pi by 2, and that is there is a force I small b capital B. And what is the direction of this force? It is directed into the plane of loop. So this represents the direction of the force F1. Similarly, I can calculate what would be the force on the arm CD, and it would be the same force but directed out of plane of paper. So direction of F1 and F2 are opposite to each other. The net force on the loop is 0, but the two forces F1 and F2 are equal in magnitude, opposite in direction, and act along different lines. These forces produce a torque which causes rotation of the coil. How do I calculate the torque? As the product of force and the distance between the direction of the force and axis of rotation. So it would be equal to F1 times A by 2 plus F2 times A by 2. So can be written as I small b capital B into A by 2 plus IB capital B A by 2. So the total force becomes I A into B into capital B. And what is small a into small b? That represents area of cross section. So the torque is equal to IAB. This represents the torque on one loop, that is one turn of the coil. If the coil has n turns, then the total torque can be given as NIAB. Now let us pick up case 2. When the plane of the loop is not along the magnetic field but makes an angle theta with it. So coil placed like this, the same coil ABCD. This represents the direction of the magnetic field. This would represent the direction of a normal. So OD represents the normal. And what is theta? Theta represents angle between the direction of magnetic field and the direction of normal to the plane of the coil. So here we define theta, angle between the field and normal to the coil. Now the forces forces on the arm BC and DA are equal, opposite, and act along the axis of the coil. They cancel each other's effect. So this force would be acting like this and this force would be acting like this. Both the forces are equal in magnitude, opposite in direction, and are acting along the axis of the coil. So they cancel each other and therefore the net force produced by them is 0. But the forces on the arms AB and CD are F1 and F2. They are also equal and opposite, already shown by us. Since they are not collinear, hence they form a couple. This generates a torque. This is what we said in the earlier part, case 1 also. But here the distance between the two direction of forces is equal to A by 2 sine theta. Correct? So that is what is the change. The magnitude of the torque is now calculated as torque is equal to force into perpendicular distance plus force into perpendicular distance, that is I into AB capital B sine theta. And torque would now be given by IAB sine theta. For a coil with n number of turns, the torque would be given by NIAB sine theta, where torque is equal to now MB sine theta. And what is small m? It is the equal to the product of NIA and is now referred to as magnetic dipole moment of the current loop. In vector form, the torque can be written as the cross product of M vector and B vector. Here theta is the angle between the direction of M vector and B vector. This equation is very similar to the case of electrostatics, where an electric dipole was placed in an electric field and we obtained the equation tau is equal to P cross E. So P was electric dipole moment and this is magnetic dipole moment. This is magnetic field and this is electric field. So analogy says that the two equations are the same form. Now what can be the unit of magnetic dipole moment? It can be written as ampere meter square and dimensions can be written as L2 a power 1. When theta is equal to 0, torque would be minimum. This indicates the state of stable equilibrium. When theta is equal to 180, torque would be tau minimum. But this would indicate the state of unstable equilibrium. Any small rotation produces a torque which increases with the amount of rotation. The presence of this torque causes the magnetic dipole to align itself with the external magnetic field. A same situation as that was encountered by us in case of electric dipole. So what conclusion really that we can draw from it? The conclusion says a current carrying coil when placed in a magnetic field experiences a torque given by M cross B. This relation is valid for coils with square, rectangular and circular area of cross section. Though it has been derived for rectangular coil, but it contains a general area of cross section. For circular coil, area of cross section would be pi r square. For a square coil, it would be side chi square, and for a rectangular coil as handled by us, it is equal to the product of length into breadth, that is small a into small b. Now, let us see circular current loop as a magnetic dipole. The magnetic field on the axis of a circular loop of radius r carrying a steady current I is given as B is equal to mu 0 I into r square upon 2 into x square plus r square power 3 by 2. What is r? R is the radius of the coil. And what is x? X is the distance along axis from the center of the loop. Distance of what? Distance of the point of observation. The direction of the magnetic field is along the axis and is given by the right hand thumb rule. Now let x be very much greater than r. If x is very large, then r square here can be neglected. If r square is neglected, then the denominator becomes twice x cube. So that is what we are seeing here. Magnetic field would be equal to mu 0 I into r square upon 2x cube. Multiply by pi and divide by pi. So pi r square would give the area of cross section, and that another pi exists here to make the things normal. So magnetic field would be mu 0 IA upon 2 pi x cube. For a coil with n turns, this would be mu 0 upon 2 pi NIA upon x cube. And what was NIA? It was magnetic dipole moment. So here it is magnetic dipole moment. So I can multiply by 2 and divide by 2. So what will I get? Mu 0 into 2m upon 4 pi x cube. Here m is equal to NIA, is magnetic dipole moment. B would be equal to mu 0 4 pi into 2m upon x cube is very similar to the one obtained for electric field of a dipole. Now just replace small m by p, magnetic field by the electric field, and mu 0 by 1 upon epsilon 0. So we get the relation E would be equal to twice p upon 4 pi epsilon 0 x cube. This gives the electric field for the electric dipole on an XCL point. Using the same analogy for the field on the perpendicular axis, we have E is equal to P upon 4 pi epsilon 0 x cube, where x is the distance from the dipole. The magnetic field for a point in the plane of the loop at a distance x would be given by mu 0 upon 4 pi m upon x cube for x very much greater than r. So what do I conclude here? I conclude a planar current loop is equivalent to a magnetic dipole of a dipole moment m is equal to Ia, which is similar to electric dipole moment P. So we are just trying to draw an analogy between magnetic dipole moment and the electric dipole moment. An electric dipole is made up of two elementary units, that is the charges or two monopoles, a positive charge and a negative charge. But in magnetism, a magnetic dipole or a current loop is most elementary unit. We do not have monopoles here. So we predict magnetic monopoles do not exist. The current loop produces a magnetic field and behaves like a magnetic dipole at larger distances and experiences a torque like a magnetic needle. This led Ampere to suggest that magnetism is due to circulating currents. A very important conclusion drawn by Ampere. It says that magnetism is due to circulating currents. मैग्नेटिज्म सर्कुलेटिंग करंट्स के कारण ही प्रोड्यूस होता है. नाउ देयर इज एन एक्सेप्शन. द एलिमेंट्री पार्टिकल्स सच एज इलेक्ट्रॉन or a proton, they carry an intrinsic magnetic moment which cannot be accounted by circulating current. इलेक्ट्रॉन जब एटम में न्यूक्लियस के चारों तरफ घूमते हैं या प्रोटॉन, उनके पास भी अपना इंट्रिंसिक मैग्नेटिक मोमेंट है जो करंट के साथ रिलेट नहीं कर सकते. नाउ लेट अस पिक अप सम एग्जांपल्स व्हिच शो व्हाट रियली वी हैव अंडरस्टूड. अ स्ट्रेट वायर 1 meter long carries a current of 10 ampere at right angles to a uniform magnetic field of 1 Tesla. Find the mechanical force on the wire and the power required to move it at 15 meter per second in plane at right angles to the field. So magnetic force is ILB sin theta. I is 10 ampere, L is 1 meter, magnetic field is 1 Tesla and the angle theta is 90, so sine of 90, which gives me a magnetic force of 10 Newton. So what would be the force required? A force would be 10 Newton. Power to move the wire is equal to product of force and velocity. So 10 Newton, velocity is 15 meter per second, so the power required would be equal to 150 watt. Now example number 2. A wire AB is carrying a steady current of 6 ampere and is lying on the table. Another wire CD carrying 4 ampere is held directly above AB at a height of 1 mm. Find the mass per unit length of the wire CD so that it remains suspended at its position when left free. Given the direction of current flowing in CD with respect to the AB, take G as 10 meter per second square. Now I can calculate what would be the force per unit length on wire CD. It would be given by mu 0 upon 2 pi I1 I2 upon D. So substituting the values, I obtain the force per unit length as 4.8 into 10 raised to power minus 3 Newton per meter. For the wire CD to remain suspended, force must be balanced by its weight. So the mass is equal to F upon G, that is equal to 4.8 into 10 raised to power minus 4 kilogram per meter. Now F can balance the weight if it is repulsive, and for that the current in CD must be in opposite direction to the one flowing in the wire AB. तो अगर आपको वायर के मैग्नेटिक फोर्स को उसके वेट से बैलेंस करना है तो आपको CD में जो करंट चाहिए दैट मस्ट बी ऑपोजिट इन डायरेक्शन टू द करंट दैट इज फ्लोइंग इन AB. नाउ लेट अस पिक अप द एग्जांपल नंबर 3. गिवन a uniform magnetic field of 100 Gauss in an east to west direction and a 44 centimeter long wire with a current carrying capacity of 10 ampere. What is the shape and orientation of the loop made of wire which yields a maximum torque on the loop? What is the maximum torque in magnitude? The torque is maximum when area of the loop is maximum. Now let us say the torque would be maximum when the area of the loop is maximum. For a given parameter, circle encloses maximum area. So wire has to be bent in the form of a circle. So let us say the circumference 2 pi r must be equal to 44, or r must be equal to 44 upon 2 pi, that is 7 centimeter. So I can now calculate what would be the area of the loop. It would be pi r square, and which gives me the area is 0.0154 meter square. For maximum torque, loop must be oriented in north-south direction. So torque maximum has a value NIAB. So multiply with number of turns is 1, current is 10 ampere, the magnetic field is 100 Gauss, can be converted to Tesla by multiplication of 10 raised to power minus 4 and 0.154 as the area. So the total torque is 1.54 into 10 raised to power minus 3 Newton meter. Now example number 4. A current carrying square loop is placed in a uniform magnetic field directed upwards. Calculate the force on the loop. So here is the figure. It shows a square loop PQRS of length L. It carries a current I in clockwise direction. The loop is placed in a magnetic field B directed perpendicular to the plane of the paper and upward, represented by dots. So must represent magnetic field perpendicular to the plane of the paper upward. Now force on conductor PQ is equal to ILB sin 90 ILB. Force on conductor QR is ILB sin 90 ILB. So all the four conductors experience equal force, but the direction of the forces are shown in the figure. On conductor PQ, the direction of the force is downward. Here it is this way, here it is this way, and here it is this way. These two forces, equal in magnitude, opposite direction, act along the same line, cancel each other. These two forces, again equal in magnitude, opposite in direction, should cancel each other. So what would be the net force? The net force will come out as 0. So an important conclusion here, a current carrying loop when placed in a uniform magnetic field experiences 0 force. Now let us pick up example number 5 to check our understanding. Calculate the force on a current carrying conductor placed in a uniform magnetic field. So what is the direction of the magnetic field? Perpendicular to the paper and inwards. Now what is the force on conductor AB? It is equal to ILB. What is the force on conductor CD? It is equal to ILB. Now what is the force on the conductor of this circular part? BCD. This is B, this is C, and this is D. So force must be equal to I into the distance between the point B and D, magnetic field B, and sin 90, and the distance between point B and D would be equal to twice the radius, so I into 2R into B. All the forces are upwards, so the total force can be calculated by adding the three forces, which gives me F is equal to 2IBL plus R. The direction of the force shown in the figure as per Fleming's left hand rule. Example number 6. A small conducting circular loop of wire of a radius of A carries a current I. So radius of the wire A, it carries a current I. It is placed in a uniform magnetic field B perpendicular to its plane such that when rotated slightly about its diameter and released, it starts performing SHM of time period T. If M is mass of the loop, then I am interested in calculating what would be the time period. So torque can be calculated here. Torque is normally given by MB sin theta. So torque on the loop is given by MB sin theta. M is the magnetic moment, B is the magnetic field. Torque can also be written as I times alpha. Alpha is angular acceleration d2 theta by dt square, and what is I? The moment of inertia. And the moment of inertia is given by mr square by 2. So I can write mr square by 2 d2 theta by dt square must be equal to mb sin theta. If theta is small, then the approximation says sin theta must be equal to theta. So angular acceleration d2 theta by dt square can be written as 2 pi ib upon m into theta. Now you can compare with the general equation of SHM. The general equation of SHM, it says d2 theta by dt square is equal to omega square theta. So what do I get? Omega must be equal to 2 pi upon t must be equal to under root of 2 pi ib upon m. So the time period can be calculated as 2 pi m upon 2 pi ib. So finally time period is given by under root 2 pi m ib. Example 7. A current carrying rectangular loop PQRS is made of uniform wire. The length PQ is equal to RS is equal to 100 centimeter and PQ is equal to RS, QS is equal to 5 centimeter. If an ammeter current reading changes from I to 2I, then find the ratio of magnetic forces per unit length on the wire PQ to wire RS in the two cases. That is FPQ for first and FPQ for 2L. So magnetic force per unit length on the wire due to RS. So F upon L would be mu 0 upon 4 pi 2 pi I1 I2 upon R. So F must be proportional to I1 I2 and in the first case proportional to I square. When the current changes to 2I, then the force F2 would be proportional to 2I ka square, that is 4I ka square. So what is the ratio F1 upon F2 equal to? That would be equal to 1 upon 4. Okay. Hope that this video explains the force on conductors clearly to you all. अगर आपको हमारे वीडियोस अच्छे लग रहे हैं तो आपसे रिक्वेस्ट है कि आप वीडियो को लाइक करिए, आप उस पर कमेंट करिए और चैनल को सब्सक्राइब करिए, बेल आइकन के बटन को प्रेस करिए ताकि आगामी वीडियोस जो आने वाले हैं उनका नोटिफिकेशन आपको सही टाइम पर मिल सके। थैंक यू वेरी मच।